La doctora Emma Fernández Alvar, que nos visita del Instituto de Astrofísica de Canarias y de la Universidad de La Laguna. Ella es colaboradora de la doctora Leticia Carigi y pues nos da mucho gusto tenerla hoy como ponente. Nos va a presentar The Emergence of the Milky Way, Latest Results from Galactic Archaeology. Y antes déjenme leerles una pequeña semblanza. Ella se doctoró en física por la Universidad de La Laguna en España y realizó su tesis en el Instituto de Astrofísica de Canarias, investigando la distribución de abundancias químicas en el halo estelar de la Vía Láctea. Tras su doctorado, en 2015 obtuvo una beca en la UNAM para estudiar la historia de formación estelar del halo galáctico con la doctora Leticia Carigi. En 2018 se incorporó al Observatoire de Côte d'Azur, no sé si se dice así, como experta en composición química estelar en colaboración con miembros del equipo de la misión Gaia. En 2022 regresó a la Universidad de La Laguna con una beca María Zambrano y actualmente desarrolla un proyecto Marie Sklodowska-Curie Action sobre la evolución de los discos galácticos, en colaboración con la doctora Carmen Gallard. Profesora en la Universidad de La Laguna, investigadora principal del grupo Galaxy Evolution in the Local Group del Instituto de Astrofísica de Canarias. Cuenta con más de 30 publicaciones en revistas científicas de alto impacto y ha participado activamente en congresos y actividades de divulgación en Europa y en América. Muchas gracias, doctora. Bienvenida.
A ti. Bueno, pues muchas gracias a ustedes por permitirme dar este coloquio. ¿Se me oye? Voy a intentar hablar alto, pero bueno, a ver qué tal. Sí que voy a dar la charla en inglés, pero sí me gustaría decir unas palabras en español al principio porque, como se dijo en la semblanza, sí que mi primer postdoc lo hice aquí, en la UNAM, en este instituto, y yo tengo un recuerdo muy bueno de esos años y para mí fue muy importante tanto a nivel profesional, el trabajo que realicé aquí fue muy bueno, muy bonito, y también a nivel personal. Siempre me sentí muy a gusto, entonces, bueno, pues nada, para mí es un placer estar aquí también y ver a todo el mundo de nuevo. Así que, bueno, esto por una parte. So now I'm going to change to English to present. So in this talk I would like to present you some results regarding the formation of our galaxy, the study of our galaxy, based thanks to the data that the Gaia mission provided in the these previous years since their launch. And okay, so a ver, let's see if this works. Bueno, vale. Okay, so in the 20 past years, the study of the galaxy has improved a lot. First, thanks to the increase of large spectroscopic surveys or large surveys of mapping the sky, like the Slow and Digital Scale Survey, RAVE, Gala, LAMOST, and there are more upcoming. So right now, the study of our galaxy is living a golden era. But what really implied a leap forward in this study has been the Gaia mission. Because, well, this is an image of the stars that was collected with the Hipparcos mission, which was a mission dedicated to measure parallaxes with a very great precision. But Hipparcos cover around 120,000 stars in a very local volume, around 150 parsecs around the Sun. And this, well, with an accuracy of 10 to the -3 arcseconds. And this was the image that we gathered with Hipparcos of the Milky Way. And this is the vision that we have now with Gaia. This is the image of the Milky Way after the third data release that happened in 2022. And as you can see, the difference is quite amazing. You can see there the Magellanic Clouds. And this clear image is because now we are mapping around 2 billion stars with an accuracy in the parallaxis 100 times better than Hipparcos. So now, with Gaia, this is just an example of why Gaia has been a revolution, because now all this data allow us to identify features in the Milky Way that it was not possible before. So first, let me introduce you a little bit about how was the classical view of the Milky Way, that it's still valid, and about what are the major components of the Milky Way. So the Milky Way has a bulge, which is not very big, a bar. These are the major components in the inner parts of the galaxy. And then there is stars moving in these kinematics with some vertical dispersion, a thick disk, and a thin disk. And then there is a stellar component. There are some stars with less density surrounding, covering a halo in the galaxy, surrounding the galaxy. Okay, I'm going to focus in these three components. So most of the stars in the Milky Way move very close to the plane. This is a plot called Tomre diagram. Here we represent in the x-axis the rotational velocity, and in the y-axis the square root of the vertical and the radial velocity of the stars. And so the thin disk stars have a quite large rotation, but they have a low vertical and radial motion. Chemically, these stars from our point of view, of course, we characterize the thin disk based on the stars that we can observe from our position, but the metallicity distribution of these stars are centered around the solar metallicity and has some kind of dispersion, but the metallicity does not go lower than -0.8 or -1. So these are the most metal-rich stars. Well, no, the bulge is more metal-rich. Okay, well, this is the distribution of the metallicity of the thin disk. And also the alpha-over-iron ratio, which is very useful to disentangle stellar populations. In this ratio, these stars have typically around solar values. So they have quite low alpha-over-iron ratios. Then the thick disk stars are stars that move also with some rotation, but they spread farther away in the plane, although they continue having they continue being more or less confined close to the plane. And chemically, the metallicity distribution function is slightly more metal poor than the thin disk, and the alpha-over-iron ratio is higher than the thin disk. And finally, the halo. Here, let me show you this simulation. The halo are stars that does not have, the whole halo does not have a net or has a very low net rotation. The stars are more dispersed and moves farther away from the plane, and the eccentricities of the orbits are higher. Okay, and chemically, so this movie that you have seen there was made from proper motions measured by Gaia, and chemically, so this. In general terms, the halo stars are more metal poor than both the thick and the thin disks, and in general, the alpha-over-iron tend to be quite high. Okay. Also, in the halo, there are some stars that move coherently or that clamp spatially, forming like streams. This is a sign that these stars, these groups of stars, are remnants of accretion events. So remnants of galaxies that were accreted in our galaxy were disrupted, but some stars maintain their dynamical coherence. Sí, it's metallicity, sí. Sorry, because you cannot see that, but yes. Okay, so the halo is a melting pot of stellar systems, and one of the questions is if the halo, all the stars come from merger of other galaxies. This was just like a summary, a reminder of what is, like in general terms, the characteristics of our galaxy. But there are some open questions still. So, for example, regarding what was the first star formation in the galaxy? The first stars formed first in an spheroidal halo, or the first stars formed already in a disk configuration? This is not clear yet. Also, the halo is totally accreted, or there are some stars born in situ in our galaxy and are there in the halo. Or again, what physical processes led to the formation of the thick and the thin disks? Which one of these disks formed before, or they form? Are they coeval? They form at the same time, or they overlap in time in their formation? And what was the role of accretion of other galaxies in the formation of the thick and the thin disks? Well, so this is like the context, and now I'm gonna. This talk is structured in two blocks. One is a brief review also of two groups of discoveries regarding the origin of the stellar halo and the early formation of the galactic disk, based on thanks to Gaia, to the data, to the Gaia data. And the second block is I hope that at the end of the first block I will convince you that there is a key parameter understanding to disentangle how was the history of the Milky Way, which is the stellar ages, the ages of the stars, and how we have now in el Instituto de Astrofísica de Canarias a project trying to provide this missing parameter. Okay, so about the stellar halo. So I'm going back to 2010. This is before Gaia, and at this point there was this beautiful work by Paul Nissen and Bill Schuster, our colleague in Ensenada, where they show that very close to the Sun, around 350 parsecs from the Sun, stars selected with halokinematics presented two distinct trends, chemical trends. One population with a high level of alpha over iron, and another one with a lower and steeper trend of alpha over iron as a function of the iron abundance. So this is important because this ratio of alpha over iron respect to the iron give us hints of how was the efficiency of a star formation in the medium where these stars form. Okay, so the high alpha population formed in a medium with a very efficient forming stars, and the low alpha population in a slower and less efficient medium. Well, okay, and these two populations were not distinct also in the alpha over iron, but also in other chemical ratios of elements that have another different nucleosynthesis. They form from different nucleosynthetic channels. So it's clear that these two populations form in different environments. Okay, And also it was very interesting to see that the high alpha population was similar to the thick disk in their chemistry. Okay, so this motivated, well, the question. Okay, could be the high alpha population this in situ halo, so the first star formation that occurred in the Milky Way before the formation of the thick disk, and the low alpha have an accreted origin. This was one of the questions, and the other, how global is this predominance? So how global is the fact that we see two populations? Are these two populations the ones dominating the whole halo, or is just something that we are seeing locally, that are dominating locally close to the sun, but the rest of the halo is different? Well, so this work motivated other works. One of them was the one that I did here with Letizia Carigi, where we infer, comparing the chemical trends of these populations with chemical evolution models, the star formation rate of the populations. And these calculations allowed to make an estimation of the possible, if the low alpha population came from a accreted galaxy, how was the mass of this accreted galaxy? Okay, so this put this show that yes, these two populations really were formed with different star formation histories. Okay, and then Gaia arrived. So first, the first data release was not very spectacular, but it allowed already to improve the kinematical characterization of stars. And this motivated a group led by Vasily Velokurov in Cambridge to investigate the CEWE survey, which is a subprogram of SDSS, that was focused, it was spectroscopic and was focused to study the halo and to see how was the kinematics of these halo stars. And here they discovered that there are, in the kinematical space, there are also two populations that dominates the stellar halo. One population, you can see my cursor more or less, one population that has some rotation, but, well, here, first, let me explain what this is. We are seeing in the y-axis the rotational velocity, and in the x-axis the radial velocity, the radial component of the velocity of the stars. And from left to right, low metallicity, from low metallicity to more metal-rich range. And what we see is that there is a population that has some rotation, but spreads very little in the radial component, and the rotation increases with the metallicity. And there's another population that has almost zero rotational velocity, but a large dispersion in the radial component. And this has no variation with the metallicity. So because this population looks like a sausage, they call it the sausage event. Okay, so this was the first data release, and then in 2018, the second data release came of Gaia, and this was really an improve in the quantity of data and also in the precision, both in the parallaxes, the proportions, so the astrometric data, but also in the photometry. So the Gaia collaboration decided to investigate, okay, let's select again stars moving with halo kinematics and see how they look like in the color magnitude diagram. And the result was that in this diagram, there are also two clear overdensities appear. So there are stars moving with halo kinematics are dominated by two stellar populations. Okay, And when investigating the chemical abundances of these populations, distinct in photometry, they coincided, they follow the two Nissen and Schuster population. The high alpha population would be the redder sequence in a color magnitude diagram, and the low alpha population, the blue sequence. Okay. So velocity in velocity space, also these two distinct populations in photometry look like, okay. So they also show differences in the kinematics, okay? And in particular, the blue sequence spread in the vertical and radial velocities, and this corresponds to the sausage event discovered by Belokurov and collaborators. Okay, so the group of Amina Helmi, which they call these Enceladus, so now this group of stars are called Gaia Sausage Enceladus or Gaia Enceladus Sausage, OGES, OGSC. Well, so they investigated this with cosmological simulations, and this is the spread in the behavior of a 5-to-1 merger event. So a satellite that merged with a Milky Way-like simulation, Milky Way-like galaxy, sorry, and they also and this galaxy merged in radial direction, so following like the plane of the disk, and this is the behavior. So this I didn't explain very well, but there's a movie that shows how this merger would look like, would be. So a galaxy merged, were accreted with a radial direction and then mixed with the galaxy. Okay, so I'm gonna jump a little bit because I'm spending too much time.
What's the mass ratio?
Is 1:5, so yes. And yes, so it was like 5 times smaller than the Milky Way by the time that it was accreted. Okay, bueno, esto, okay. Vale, so this regarding the blue sequence, but what about the red sequence or the high alpha population? So several works investigating different things, but I think this one showed better this effect. What was the conclusion was that this high alpha population with halo-like kinematics was just the result of stars moving already as a disk by the time of the accretion of Gaia Enceladus sausage, that because of the merger were heated, these stars. So now they are in the halo. And this, you can see here that at a certain metallicity, you have stars rotating, like in a disk, but also a dispersion, a tail, towards not rotating stars and even counter-rotating. And the thing is that they all have the same metallicity, okay? So it's like a fraction of stars that were moving in a disk were heated. But, okay, I'm gonna jump. Okay, so right now, this was one of the big results thanks to Gaia. And this group of stars not only clamp in chemistry, in kinematics, but also in this space, in dynamical parameters. No? If we just show the energy with respect to angular momentum, these stars, the Gaia Enceladus, would be this blob, which is the most prominent. But there are other blobs, and now people try to identify more accreted events based on the clamps in this space. But one of the questions now is, okay, maybe these stars that clamp in this space in several regions might be not each one a single accreted event, but they are related and they come from the same event. Well, it's okay. It's how it's the state of the art of this. Okay, about the early formation. Another discovery, thanks to the increase of the accuracy in the kinematical parameters, thanks to Gaia, is the discovery of extremely metal-poor stars moving in disk orbits. Why is this interesting? First, because as I showed you before, up to now, when we were analyzing the metallicity distribution of stars moving in the disk, the low metallicity tail didn't go very low in metallicity. They didn't go for the thick disk, lower than minus 1.5. There were some claims a bit lower of a metal weak thick disk, but well, this is one thing. And the other thing why this is surprising is because in cosmological simulations, the theoretical models predict that at the earliest stages of galaxy formation, there was a high merger activity. So there were a lot of mergers going on, and even if there could be some star formation in a disk configuration, because of the mergers, these stars wouldn't last too much as a disk, because they would be heated very soon. So this is what the models predict, but what nature is telling us? What nature is telling us is that we find stars with metallicities lower than minus 2.5 that move as a disk. I'm going to explain you this plot where we are seeing this. So here, instead of velocities, what is shown is they are actions of motion, which are invariant with time. And in the y-axis, what we see is the action corresponding to the vertical motion of the stars, and in the y-axis, the rotation. So this is a plot for stars with metallicities lower than minus 2.5, so extremely metal poor. And here, the stars that move like the thin disk would be the ones around 1, because this is normalized to the solar motion. So the thick would be here, and the halo would be populating everything, and stars moving also in planar orbits, but with a retrograde rotation would be the ones with negative values. Okay, so the thing is that the fraction of stars moving as a prograde disk is not small. Okay, this was like the first work showing this. Then, when I was in Nice, in France, we investigated using data from a survey called Pristine, which was dedicated and is still dedicated to target very metal-poor stars in the Milky Way, but they also observe metal-rich stars. Well, investigate the relation, the distribution of rotational velocities as a function of the metallicity. Okay, and this was this was a sample of stars towards the anticenter of the galaxy, because for these stars we had more measurements of rotational velocities. Well, I'm not going to explain this, but well, it was towards the anticenter. And here, the thin disk would be stars here, where we see the majority of the stars. The thick disk would have a slightly lower rotation. And then you see here like this spread, which would be the splash, the heated thick disk, and the halo. But what was interesting here is to detect this group of stars, this extension of stars rotating like the thin disk, but spreading towards low metallicities. ¿Vale? Okay, so what was the weak point of this work? That the metallicities measured for these stars came from, or come from photometry. These are metallicities calculated from a calibration of photometric data with spectroscopic measurements. And although for very low values, below -2, the metallicities inferred are very good, at higher metallicities, the method starts to show more uncertainties, and there could be some contamination of stars here in the region that would be, in fact, more metal-rich. So this was a bit uncertain, but so that's why we investigated also spectroscopic surveys of high resolution, from which we have more reliable metallicities. And the thing here, well, in this work, we were more focused on analyzing stars really like the thin disk, with very low eccentricities and rotating like the sun. And here on the left is more or less, well, it's also an action space. So here, well, in the x-axis is again the action corresponding to the rotation, and in the y-axis is the composition of the vertical and the radial motion. So here in this plot, the stars moving like the disk would be the ones on the right with zero, well, in this vertex. Then stars moving close to the plane would be the ones following this side and also this side. And the thing is that from this point, this vertex along this side, the eccentricity increases. Okay, so the orbits move forward from very circular orbits to more elongated orbits. And here would be the retrograde, stars moving with retrograde motion. So we selected the very, very vertex, so the ones moving more in circular orbits, and this is the metallicity distribution function. Well, we cut it at -0.5 because we wanted also to explore the low metallicity tail for these stars. And yes, so we saw evidence of stars down to even -2, but the reality is that in very few numbers, okay? Okay, so then the questions that arise are, okay, the fact that we see very few number of stars like this is telling us that maybe this is just the fast rotation tail of the global halo distribution, because the halo velocity distribution, okay, the net rotation is 0, but there is a dispersion of the velocities, okay? So maybe just selecting these stars here, we are just gathering the stars that are in this fast rotating tail of this global distribution, okay? But the thing is that we really see an overdensity of stars, not only with circular orbits, but with prograde orbits. Could this be that this is just a tilted halo? Still, the fraction of stars is quite high. Others also thought, okay, maybe these were stars that were also part of the halo, but were pushed because of the dynamical effects of the bar. But, well, this is because a lot of works were beginning to work on this, and there were some publications following this. So there was also a work trying to quantify what would be the fraction of stars affected by a bar, and still too low to quantify for this overdensity of stars there. So could this be the remnants of an accretion event, also in some direction that favor that now these stars move like the disk of the galaxy? Or could this just be the first star formation in a thin disk configuration? And how is this related in time with the formation of the thick disk? Well, this is an open question. I would like also to show you another important result, again led by Vasily Velokurov, where they used kinematical criteria to say, okay, these are stars formed in situ in the galaxy, and these stars are accreted. And the criteria was the aluminum over iron ratio. Why aluminum? Because, well, aluminum, because it is expected that also the aluminum over iron would be affected by the star formation efficiency of the medium, and there would be differences. And in particular, in the Milky Way, the level of aluminum is expected to be higher than 0. So they used this criterion. They selected the stars with aluminum higher than 0 at low metallicities to say, okay, these are in situ stars, and the ones that with negative aluminum over iron are accreted. And it turns out to be a quite good, well, at least the in situ selected stars follow well like a high alpha over iron ratio. This is the magnesium over iron. Well, it looks like a quite fair criteria. Okay, so with these in situ stars, they analyzed the tangential velocity of the stars, which is, again, more or less like the rotational velocity component that we were looking before, and how this evolves with the metallicity. And what they concluded is that below minus 1.3, well, here it's not so clearly seen, but in the paper, if you read it, their conclusion is that below minus 1.3, there is no evidence for the existence of for stars moving like a disk, and is there at minus 1.3 to minus 0.9, where stars, where we see like the spin up of the disk of the Milky Way. So they call these stars below minus 1.3 like the in situ halo, okay? Because based on the chemistry, they could be considered formed in situ in the galaxy, but the kinematics don't look like a disk, okay? Yes. Sí, sí.
Just to clarify, when you say in situ, or the authors say in situ, this means that these stars were not formed within galaxy satellites or the Milky Way, but from the intra-halo gas, directly from the intra-halo gas.
Exactly.
Molecular clouds that could form in and then form stars.
Exactly.
Wow.
So from gas accreted, yes, but the star formation occurred already in the Milky Way. I don't remember exactly. I think it's within the virial radius of the Milky Way. Well, I guess it's closer than the center of the Milky Way, yes, because the virial radius is quite large, right? But yes, from the gas, yes.
Okay, thank you.
But there's a lot of debate, okay? So it's a really an open question. I like the state of the art of where are we and what is motivating in investigation right now. Okay, so what is missing here? What can we can really help to disentangle, maybe not to clarify completely everything, but just to provide more information and more constraints about how the story was, is the ages, okay? The stellar ages. Because this allows us to evaluate how the different kinematics and chemical properties evolve with time, okay? For the different components of the Milky Way. But what is the difficulty right now? To infer stellar age, right now what we need is to compare with isochrones, okay? And for that, we need high precision in stellar parameters. So the precision of the age is enough to disentangle different events, okay? In other words, if we need a spectroscopy to have high precision in the stellar parameters, so the uncertainty of the ages is good to see a clear picture, okay? And the thing is that right now, the uncertainty of the ages makes things a bit blurred still. Okay, so this is an example, maybe with this you understand better what I'm trying to say, of age metallicity relations inferred with the ages that are computed and the metallicity measurements, okay? And the thing is that, yes, we here see some trends, and with this we are inferring information, but still everything is a bit blurred, okay?
Is only Gaia stars or also?
These are stars with spectroscopic parameters, so these have Gaia counterparts, because these works, I think they use Gaia photometry, but so Gaia is a photometric survey, so the number of stars is very large, and spectroscopic surveys have a lower number of targets. So the database is lower. So then it's like a subsample of Gaia. And also, you need to be restricted to the main sequence turn-off and subgiants part of the CMD, because there is where the stellar evolution splits and the age. So the photometry allows us to, I don't know how to explain this, but yeah, the isochrones splits more, and then it's easier to identify. Yes, there are less. It's less degenerated, the problem, and the age can be inferred better. Sorry, I'm not explaining myself very well, but okay. So the point is that even is a subsample of spectroscopic surveys, which are a subsample of Gaia. Okay, so the point is the number of stars for which we have more or less precise ages is low, ¿vale? And the samples are not complete. Okay, they are always biased. So there is a lack of accurate ages for large distribution of stars. Okay, so, and here's where the Chronogal project appears. This is a project led by Karma Gallard, who is an investigator in the Instituto de Astrofísica de Canarias, and she tries, well, the project aims to apply the CMD fitting technique, which consists on compare the observed CMD of a stellar population or a galaxy, or a part of a galaxy, a component of a galaxy, whatever, with a CMD computed, a theoretical CMD, populated by a lot of single stellar populations. Each single stellar population is a group of stars that form following an initial mass function at a particular age, with some dispersion in age and a particular metallicity. It's not an isochrone because it has some, it covers a narrow range of age and metallicity. And you populate all your CMD with a lot of these single populations, ranging from very old to very young ages, and from very metal poor to very metal rich ages. Okay, and then you make a statistical comparison of your observed CMD and try to find what is the linear combination of single stellar populations that best reproduces your observe CND. So in this way, if you have a whole system, like a nearby galaxy where you can see all your stars, then you can infer with this method the star formation history of your whole system. So, well, in the case of the galaxy, of the Milky Way, the problem, we are not seeing the whole galaxy, okay? We see like a part of some population in the galaxy, okay? So maybe, so this technique was widely used in nearby galaxies, and now is applied in the Milky Way. It was not possible to apply it before because for this we need very, very good distances, very good parallaxes to compute the absolute magnitudes. And until Gaia, this was not available in the Milky Way. It was available in nearby galaxies because there you have some standard candles that provides you a distance estimation, and then the differential distances of the individual galaxies are very small. So you can consider this measurement for the whole galaxy, so then you have good seeing this. But for our galaxy, it was not possible until now. But now with Gaia, yes. Okay. The star formation history maybe is a bit tricky, or their interpretation is not trivial, but what provides this method is the distribution of the ages and the metallicities of the stars that we are observing, of our CMD. And this is already a big leap forward in the computation of ages, okay? Also because Gaia is quite complete until a certain magnitude, so then we can see like complete populations until a certain distance, and then the age distribution that we obtain is quite complete also, okay? So here I will show you the proof of concept of this technique that was published last year. I'm going, okay. I'm almost finishing, okay. And this is the age metallicity distribution of stars around 100 parsecs around the sun. And for comparison, there are other age metallicity relations infer with the star force, which is another, I need to finish, right? Okay, vale, okay. I can finish here, but just, I had more...
I think you have 5 minutes.
5 minutes, okay, perfect. Okay, so this is a comparison of, with this technique, we infer ages with higher precision than other techniques for more complete samples, and then this allows us to see more details in our stellar populations that we are observing. And this is the comparison of our metallicity distribution function that we obtain with very precise measurements from spectroscopy. So this is very reassuring that we are inferring this with very high precision. And if we add the typical errors in metallicities and ages that measure for other groups, so then we recover something very similar like the others are. So it's really a matter of precision that we are obtaining higher. Okay, so what we did, I'm going to pass this very fast, is to, in in a cylinder close to the plane, with a height close to the plane, we selected kinematically stars with thick disk and thin disk orbits, and we inferred the age and metallicity distributions for these stars. And this is what we obtained. So what we obtained is that most of the thick disk stars have ages older than 10 gigayears, and most of the thin disk ages larger than 10 gigayears. And 10 gigayears was the age where it was estimated that the merger with Gaia and Enceladus occurred. So this is quite well, interesting because it's like the pass in the Milky Way from thick disk to thin disk is somehow related to Gaia and Enceladus accretion. Maybe because it was the last major merger, and only after that it was possible to form stars in really cool orbits, like cold orbits, like a thin disk. The other interesting thing, well, okay, so there are some cosmological simulations that predicts that because of the pericenter passages of a merger, a galaxy that is being accreted, some star formation are induced in both in host and in the accreted galaxy. And what we see in the thick disk is that there are like 3 episodes or 3 globes of star formation, and we hypothesize, but we are still investigating, if at least the second and third group of stars could be star formation induced because of the pericenter passage of Gaia and Enceladus. There's also a group of stars with thick disk kinematics, but much younger ages. And 6 gigayears is the time where the estimated time for the first pericenter passage of Sagittarius. So it could be that the Sagittarius also induced star formation in gas that was heated by their passage, or maybe stars already formed but that were heated to thick disk orbits. Bueno, this I'm gonna tell. And for the thin disk, well, here the picture is more complicated, but what is, so because we see here stars of thin disk kinematics, but at all ages and all metallicities, because it's true that most of the stars have ages younger than 10 gigayears, but we see again here like very metal poor stars, but very old in thin disk orbits. And also the other thing that I would like to point out is that at some ages we see overlap of populations with different metallicities. And this, in our opinion, is like a sign that we are seeing here signs of radial migration, and also stars that maybe were born in the inner or in the outer disk, but right now they are passing through here. So yeah, it's a bit more complicated to disentangle this. And that's it. Okay, yes, hang on. So this is the final step, and I'm gonna answer questions. Okay,
Thank you, Emma. Thank you. We thank our speaker. Questions? Vladimir?
Thank you, Emma. Thank you, Emma. Very interesting results. Regarding these star formation histories, is it possible to know how this star formation history depends on the radius, on the galactocentric radius? It was more peaked in the center and more extended in the periphery or something like that?
Okay, so to do that, because the caveat of this method is that we don't have ages for individual stars. So we cannot follow the kinematics or the chemistry of these stars. We just have the global distribution. But what we can do, and we have already done it, but I cannot show you here this, I don't have it here, is to select, to make another kind of relations, for example, based on the guiding radius, yes, and to infer the age distribution for these stars. So yes, it's possible. Yes.
Yeah, the problem is the filling factor, yeah, you say, because you are sampling only.
Exactly.
Yeah, okay.
That you need the samples to be complete. So sometimes this is the difficulty.
Questions?
Very nice work, very nice talk too, because I learned a lot. One thing, one question. you identify that in the 10 gigayear event kind of divides the thick disk population at low metallicity and the thin disk.
Yes.
Since your single stellar population models have solar relative abundances, what would be the, I mean, of course you cannot estimate it, but what's the order of magnitude of the error on the age derived from that method, especially in the old population where the alpha over elements are higher?
Yeah, very interesting question. So the thing, so this is something that we ask us too, because a priori, yes, we don't have, well, okay, I'm going to answer this. So the thing is that we infer not iron, but metallicity. And the thing is that the tests that people that work, well, in particular Santi Cassisi, which is our expert in stellar evolution, says is that even if you use alpha solar scale or alpha enhanced stellar populations, in metallicity, the difference in photometry from one model to another is so low that the impact is really negligible. So this is what, so in iron, yes. Well, if the photometry is the same, yeah, I don't know. It's my knowledge. So the opinion of the expert is that there's no impact, but I cannot tell you. I don't know. But it's a very interesting question.
Are there questions in internet?
In Zoom, someone wants to ask something?
No?
Thank you. Thank you very much. Now I can figure out some questions to my students,
Okay.
in the sense that I can ask how many things you can enumerate that are new about the Milky Way that you didn't know about 10 years ago, for
Yes.
example. So things are changing very rapidly and very impressively.
Yes.
And my question is there any estimate that you could make for the stellar halo in the sense of the star formation history? For the
Yes.
stellar halo?
Yes. So in fact, this is another work. There's another publication by González Coda but I think he only showed, also with, he's part of this team, but I think he only analyzed stars selected to belong to Gaia and Enceladus. But yes, it's possible to infer the star formation history for the whole halo. And I don't have here, but yes, so the thing is that, yes, it's very old. We see also like the two populations. We see more than two blobs of star formation. But for, so for the early halo is quite, so we see like the heated disk. And this heated disk has a metallicity that is like this. And then we have Gaia Enceladus, which is located more or less like this. Okay. So the difficulty in the halo is that, and with this method, is that if you have stars, very few stars, a population of with an age and a metallicity, but that is very low, maybe you cannot detect it with the method if it's too low in number. So because of the halo, there are less number of stars, and is dominated by these two populations, the Gaia Enceladus and the heated disk. If there are other star populations that are very minor, it's more difficult to detect them. So, yeah.
Yes. Yes, can you hear me?
Yes.
Yeah, okay. So that's really, really interesting, your talk. So you find this very clear change in between the thick disk and the thin disk. The thin disk doesn't only appears after 8 million years, 8 gigabyte years, right? And before you have the thick disk, and your interpretation is that this major event triggered the formation of the thin disk, right? But could it be that the major event could disrupt the thin disk? Now, the older stars are the former thin disk and now appear in the thick disk because of the dynamical interaction,
Yes,
right?
yes, yes, yes. It could be. Yes, so my interpretation is not that the major event induced the thin disk, but that allowed stars form in cold orbits. Because if there are mergers, this is hitting the things. But yes, maybe the thick disk, the younger thick disk, because some thick disk we expect an old thick, well, we don't know. Yeah, but yes, exactly. Could be a thin disk first, and then this was heated because of the mergers, and now it's thick. Yes.
I have a last question.
Yeah.
Well, it is known that the Gaia-Enceladus merger induced the formation of the thick disk, as far as I know.
Uh-huh.
So this now Milky Way accreting the dwarf Sagittarius galaxy. Are there simulations that show the impact of this merger on the disk, or it is not going to be such an impact in the disk populations?
But I'm not an expert on Sagittarius, first of all. Second, so what is clear, also thanks to Gaia, is that Sagittarius is creating a dynamical effect in the disk, like the warp, some, well, maybe the dynamicist can...
The morphology.
Yes, about the morphology. If there is star formation induced by this, we need to still investigating. But there was a work by Tomás Ruiz Lara also using this methodology, but with a previous code, not so fancy or whatever, that, yes, apparently some peaks of star formation appear, coincide with the percenter passages of Sagittarius. But I think it's soon to make strong conclusions, and more investigation has to be...
Or more data, maybe. It is needed
Yes.
from Sagittarius. Thank you. Any other questions? No?
I would like to make a comment,
Okay,
first comment,
go
sorry,
ahead.
because I
Go
forgot.
ahead.
So why I am here now, and it's because, just very fast, it's because, so now what the next steps is to try to use chemical evolution models using some of the information that we gather with this, especially for the thick disk, because we consider that the star formation history that we obtain for the thick disk could be more representative of the whole thick disk, and to use chemical evolution models to constrain the inflow of mass that would be necessary, inflow and outflows, to that occur to form the stars of the thick disk. And this is what I came to, and we started this month that I was visiting the IA with Leticia, and that we will continue working on in collaboration. That's it.
Thank you. We thank
Thank you.
again our speaker.